Okay, Spartan fans, so today you're going to learn about parent functions. So you should have gotten two gold sheets from the substitute, and one of them looks like this screen that you see here. These parent functions are incredibly important, and your ability to graph them is going to carry through all of your math life. So first we're going to look at the absolute value graph. And the absolute value graph is y equals the absolute value of x. And remember, we learned that for absolute value, whatever is the output must always be positive. And so I'm going to talk to you today about these things called parent points. And I use parent points all the time when I graph. And I'm going to start by making a little t-chart here for x and y. And I always pick the same 5 points: -2, -1, 0, 1, and 2. And you can pick any points you want, but I feel like having a couple positives, a couple negatives, and 0 is always a good place to start. So if you plug in -2, the absolute value of -2 is 2, and the absolute value of -1 is 1, and the absolute value of 0 is 0, and the absolute value of 1 is 1, and the absolute value of 2 is 2. And so I'm going to plot these points: -2, 2, -1, 1, 0, 0, 1, 1, 2, 2. Use a ruler, draw a nice graph. The absolute value is a V. That's how you can remember what it looks like. Absolute value is a V. That doesn't look very good. Let's draw it again. There we go. The domain and range. The domain is going to be all real numbers, and the range is going to be 0 to infinity, and 0 is a bracket because it is included. The x-intercept is at the origin, which means the y-intercept is at the origin. And that is the graph of y equals the absolute value of x. Okay, quadratic, here we go. Quadratic, y equals x squared. And again, same thing, I'm going to pick the same parent points. And I'm going to pick -2, -1, 0, 1, 2. -2 squared is 4. Be careful, it's -2 quantity squared is 4. -2 squared without the parentheses is -4. So they're a difference. -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. So when I plot these points, 0, 0, -1, 1, +1, 1, looks very much like an absolute value graph until we throw on the 2, 4. Oh, I hate when the iPad does that. Let's try again. It's called a parabola. The domain, same exact domain and range as the absolute value function. X-intercept, y-intercept, the origin. Okay, square root function we might be getting into some functions you haven't seen yet. Square root function, y equals the square root of x. And I'm going to choose the same points again. -2, -1, 0, 1, 2. And this is the first function now where we get into some issues with these points. Square root of -2. Nope, can't happen. Square root of -1. Again, can't happen. Square root of 0 is 0. Square root of 1 is 1. The square root of 2, if I used my calculator, it would say like 1.4, but that's not a really easy point to plot. So instead, I'm going to create a little extra table here, and I'm going to plug in 4 because I know the square root of 4, and the square root of 4 is 2. And I'm going to plug in 9. I know the square root of 9. The square root of 9 is 3. The domain here is going to be different than the previous two functions. So it's going to go through the origin and 1, 1 again, just like the other two. But now 4, 2 is here. 9, 3 doesn't fit on my graph. And this is half of a sideways parabola. The domain must be positive, 0 to infinity. The range is also 0 to infinity. And the x and the y intercepts are at the origin. All right, moving right along. Cubic, excuse me, the cubic function, y equals x cubed. I bet you can't guess what points I'm going to pick to plug in. Okay, so negative 2 cubed is negative 8. Negative 1 cubed is negative 1. 0 cubed is 0. 1 cubed is 1. 2 cubed is 8. Again, it goes through the origin. So 1, 1, 2, 8, I don't know. I mean, just for the sake, I gave you this really super small graph. The right half of the parabola goes up, and the left half of the parabola goes down. And that is what a cubic function looks like. You can cube any number you want, and you can get a result. The domain and range is all real numbers. All right, cube root actually is going to be an inverse function. So the cube root is the inverse of a cubic. And so we're going to have y equals the cube root of x. All right, here we go. Parent points. Negative 2, negative 1, 0, 1, 2. Cube root of negative 2. It exists. It's some number on my calculator, but I don't know what number it is. The cube root of negative 1 is negative 1. The cube root of 0 is 0. The cube root of positive 1 is 1. Cube root of 2, I don't know. It's some number on my calculator. So a better number to plug in would be negative 8 and positive 8. You can cube root a negative. You can odd root. Cube root, fifth root, seventh root, negative 2, positive 2. Okay, and then just like for the cubic, it didn't really fit on my graph, the cube root, 8, 2, well, I don't know, somewhere around here. So if you look at just the first quadrant, it's in square root graph, but then I've got this other piece that goes like such. Domain, all real numbers. Range, all real numbers. Did you notice that every single one of these graphs goes through the origin? Every single one of them. 0, 0, 0, 0, 0, 0. 0, 0, 0, 0, 0, 0, 0, 0. All of them. Origin, origin. But, origin, origin. Now, I'm going to mess you up, because we're going to do this last parent function. It's the reciprocal function. It is often referred to as a rational function. You're going to hear it called the rational function more often than you're hearing it called the reciprocal function. And so that is 1 over x. So this function causes a problem because when I do my typical parent points, negative 2, negative 1, 0, 1, 2. Okay, so I'm just going to expand this just a little bit so I have more room to write. So when you plug in negative 2, you get 1 over negative 2. That's negative 1/2. When you plug in negative 1, you get 1 over negative 1. That's negative 1. And when you plug in 0, you get 1 over 0. Absolutely not. Never, ever, ever in your entire math life, you can never divide by 0. Ever. There's no exception to that rule. You can never divide by 0. Division by 0 is undefined. And so you'll notice we have this thing called an asymptote. And there's an asymptote at x equals 0. And an asymptote, a loose definition of an asymptote, is a line the graph approaches but never touches. It is a line that the graph approaches but never touches. So if I plug in negative 2, I get negative 1/2. If I plug in negative 1, I get negative 1. And then I can't plug in 0. That is not allowed. I can plug in 1. If you plug in 1, you get 1. And if you plug in 2, you get a half. Kind of ran out of room here, so I'm going to have to erase this eventually. But so if you plug in 1, you get 1 over 1, which is 1. You plug in 2, you get 1 over 2, which is a half. And so that's how I got those points that I just plotted. And this is really funky to look at. So you have this thing called an asymptote. It's a dotted line. So when x is 0, that is actually on the y-axis. So I can't really draw it exactly on the y-axis, so I'm drawing it off to the side. So notice the x-intercept and the y-intercept. This is really, really funky. Okay, so I want you to think about this for a second. I want you to answer this question. What number can I plug in for x? So if I'm making my t-chart here, what number can I plug in for x that's going to make y 0? If I plug in 1, do I get 0? No. If I plug in 2 or 3, if I plug in a negative number, am I going to get 0? If I plug in a fraction, if I plug in a decimal, if I plug in positive numbers, I don't know. And the answer is there isn't a number. There is no value that you can plug in for x that's going to make y 0. So there is another asymptote, and this asymptote is also at y equals 0. So there are two asymptotes, x equals 0 and y equals 0. And this graph is also referred to as having branches. So it's a rational function. And these are called branches. Okay. Okay. I want you to actually go to the last page with the transformations, and then we're going to come back and do the last graph. So I want you to go to the second page that the sub gave you, and we're going to look at the transformation guides. Okay. I put it on gold paper because it's super important. So transformation. Okay. The f of x plus h. H tells you a horizontal shift, horizontal left, right, and it's always the opposite of what you would think. So it says x plus h, that's actually a shift left units, however many units it's going to be. And x minus h is going to shift the function to the right. Plus k, this is going to shift the graph up. And minus k is going to shift the graph down. Okay, so here's what I mean. Now go back to your other page. So notice that in this row of problems that we're going to graph together, all of them say plus 4 inside the parentheses, or plus 4 underneath the root, or plus 4 in the denominator. That is going to shift the parent function. This is going to shift the parent function left 4 units. And here's a way that you can think of this. Normally these graphs go through the origin. Most of them do, at least. Not all, but most. If I want to create a new origin point, what number plus 4 is 0? Negative 4, and negative 4 is to the left. So this is going to be shifted left 4, all of them. Okay. The minus 3 for each one of these, they all say minus 3. And that's outside of the parentheses or outside of the root or on the side of the fraction. That's going to tell us that we are going to shift this graph down 3. So all of these are shifted left 4, down 3. I need to erase this. Okay, so here's what I'm going to do. So normally, x plus 4 cubed minus 3. The parent function is x cubed. And we're moving this x cubed graph left 4, down 3. Okay, so I'm just going to draw it here. I'm just going to kind of sketch it in. X cubed. We just did it. So x cubed was, this was x cubed here in green. And we said it went through the points 1, 1, 2, 8, -1, -1, and -2, -8. So that was my cubic function. So what I'm going to do is, here's my cubic function. So I'm just going to kind of draw it in dotted. That's my x cubed. But I'm going to shift this left 4, down 3. So my origin point right here, I'm going to move that left 4, down 3. And that's here. So this is my new origin point. Oh, darn it. I hate when the iPad does that. If you think of this as your new origin point, so I kind of drew in a new x and y axis, this process works for every single parent function and it works for every single shift. If you think of this new origin point right here, if you think of that as your 0, 0, and from here you plot your parent points, so the parent points were -2, 8, -1, -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. Those are the parent points for x cubed. How do I know that? We just put them in the table. Those are the points that we got right here. -2, -8, -1, -1, 0, 0, 1, 1, 2, 8. That's what we just did. So if I'm taking this graph and I'm moving it left 4, down 3, and I think of -4, -3 as my new origin point. So from my new origin point, I'm going to go right 1, up 1, right 2, up 8, -1, -1, that's left 1, down 1, -2, -8, and that is how I'm going to find my new points. And there's your graph. I'll highlight it so we can see what it actually looks like here. So I'm going to use this same concept of a shifted origin to help me graph the cube root of x. So the cube root of x, and you'll get good at this. I mean, you're not going to be good at it today. The parent function is the cube root of x. And the parent points for the cube root of x were -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. Those were from the cube root of x, which was right here. There's the cube root of x. Okay, so I'm going to shift this graph left 4, down 3. So I'm going to move left 4, 1, 2, 3, 4. Here's my new origin point. Put a little star there. So instead of my origin being here, now my origin is right here. And if it helps you, draw in a dotted XY axis. And so from this new origin point right here, I'm going to plot the point 1, 1, 8, 2, -1, -1, -8, -2. So you might be thinking, can't I just make a table of values and plug in? And the answer is eventually that's going to cause you, you're going to have 10 minutes on a quiz and all of a sudden it's going to take you 15 just to make the table of values. 1, 2, 3, 4, 5, 6, 7, 8. Let's see here. 1, 2, 3, 4, 5, fits. Oh, I'm not sure, it barely fits. And there's the graph of the cube root of x plus 4 minus 3. You know what? We can always plug in a point to check. So for example, this point right here that I'm highlighting, that point is actually 1, 2, 3, negative 3, negative 2. The actual point on the graph is negative 3, negative 2. Let's check. Plug in negative 3 for x, plug in negative 2 for y. Is it true that if y is negative 2, and you take the cube root of negative 3 plus 4 minus 3, is that a true statement? I'm pretty sure it is. Negative 2, cube root of 1 minus 3. Negative 2 equals 1 minus 3. Negative 2 is negative 2. We've done it right. I'm showing you this method because it works for all parent functions for all the shifts. Okay, now let's do the rational function, which has branches. So I'm moving left 4 down 3, and that's going to be my new origin point. But the difference is the rational function, so that was drawn right above. The rational function, that's right here, right above. It's got these branches. It doesn't go through the origin. Oh, I totally forgot to do the domain and range. I apologize. We'll go back to that. Since we're here, let's do it now. No x-intercept. No y-intercept. The domain, all real numbers, x can't be 0. The range, all real numbers, y can't be 0. Okay, so notice that this graph, it doesn't go through the origin, but the asymptotes intersect at the origin. So instead of moving, a certain point, I'm moving my asymptotes left 4 down 3. So left 4, 1, 2, so that's going to be here. My horizontal asymptote is at negative 3. And then from here, so my parent points were 1, 1, 2, 2. I'm sorry, not 2, 2. 1, 1, 2, 1 half. So 1, 1, 2, 1 half. So from my shifted origin, here's my origin, left 1, down 1, left 2, down a half. And there you have it. Okay, so let's go back to, I know I'm having you shuffle around a lot. Let's go back to the second page, which was these transformations. So notice I left part of this blank because we haven't gotten there yet. Okay, we have these things called dilations. Okay, so A is the coefficient, that's a fancy word, coefficient, on the function. Okay, so when the absolute value of A is greater than 1, we call this a vertical stretch. And when the absolute value of A is less than 1, we call that a vertical compression. And if A is negative, this is a reflection over the x-axis. Okay. When I'm back in class, the next time I see you, I'll give you a visual of what a stretch and a compression looks like. It's hard for me to do on a video. Okay, so here we go. So go back to your previous page. we're going to look at the transformations of these last three functions. Okay. Okay, so all of these, notice that every single one of these, -1 plus 2, -1 plus 2, -1 plus 2. And they all have a -1/2, -1/2, -1/2. All three of these graphs have the exact same shift. The difference is their shape. So this first one, this is going to be shifted right 1, up 2. It is going to have an x-axis reflection. And the -1/2, the absolute value of -1/2 is +1/2, and that is going to be a vertical compression. All of these. Right 1, up 2, reflection, compression. All of these. Okay, I'm not going to write it the last time. So all of these are going to have a shifted origin at right 1, up 2. So for all of these, that's what I'm going to do. Right 1, up 2. So here's my shifted origin. Right 1, up 2. Right 1, up 2. All of them. Okay. This first graph is a x squared. That's a parabola. The second one is a square root function. That's half of a sideways parabola. And the last one is absolute value. That is a V. So that's what my parent function looks like. Okay, how do I take care of the -1/2? All right, this always, always, always works. Whatever A is, okay, so A is -1/2. Always, you're going to take your parent Y values, only the Y values, because it's dependent on X. You're going to multiply your parent Y values, and you're going to multiply them by whatever A is. I don't know my parent points. You will, and I'm super confident. You know how I always pick -2, -1, 0, 1, 2? You're going to get really good at plugging them in off the top of your head. Okay, so I'm going to go to the parabola. My parent point, -2, 4, -1, 1. You don't need 0, 0. Everything's going to be 0. 1, 1, 2, 4. And I'm going to multiply my Y values only, my parent Y values. I'm going to multiply those by A, and in this case, A is -1/2. Okay, so the point -2, 4 is going to become, I'm out of room. I write too big and I don't leave you enough space. This point is going to become -2, 2, because 4 times -1/2 should be -2. -1, 1. The Y value is 1. 1 times -1/2 is -1/2. The point 1, 1. X stays the same. Y is 1 times -1/2 is -1/2. 2, 4. 2 stays the same. Y value is 4, multiply it by A, which is -1/2, and you get -2. So from my shifted origin, okay, so from my new origin point, so here's my origin. I'm going to plot these new points. -2, so -2, -2. From here, -2, -2. -1, -1/2. 1, -1/2, 2, -2. And this is going to take care of my shift and my reflection all at once. And this is considered a compression. it's a wider. It is a wider graph. So I'm going to do the exact same thing with my parent points for the square root function. So the square root function, parent, square root of 0 is 0. Square root of 1 is 1. We don't know the square root of 2. We don't know the square root of 3. Square root of 4 is 2. Square root of 9 is 3. A is negative 1/2. 0, 0 stays the same. 1, 1 becomes 1, negative 1/2. 4, 2 becomes 4, negative 1. 9, 3 becomes 9, negative 3/2, which of course isn't going to fit on my graph. So from my new origin, which is here, here's my new origin, my parent points, my modified parent points are 1, negative 1/2, 4, negative 1, and then 9, 3 doesn't fit. Well, 9, negative 3/2. Okay, last one. Okay, absolute value is a V. Parent points. I am very confident that you can create the parent points off the top of your head. Absolute value of negative 2 is 2. Absolute value of negative 1 is 1. 0, 0, who cares? Absolute value of 1 is 1. Absolute value of 2 is 2. I'm going to multiply only the y values by a, which in this case is negative 1/2. The x doesn't change. Y is negative 2, or y is 2. I'm going to multiply it by negative 1/2. That's going to give me negative 1. Negative 1, 1 becomes negative 1, negative 1/2. 1, 1 becomes 1, negative 1/2. 2, 2 becomes 2, negative 1. Use a ruler. It is reflected. It is a vertical compression, meaning it's wider. Okay. So let's just fill in a few more things here. A vertical stretch, essentially, it's not politically correct. A vertical stretch means the graph is skinnier. And a vertical compression means the graph is wider. Okay, I want you to pause the video and I want you to take a minute and I want you to fill in 1 through 7, compare with your neighbors, and when you're ready, push play on the video and see how you did. Left 2, up 2, right 2, down 2. This is skinny. This is called a stretch. And this is a compression. It's wider. And the negative absolute value of x is a reflection. Okay, it's a long video. There is a homework worksheet that you should get from the sub, and I will go over homework with you next time I see you.